So on the boards over here, I was just recapping some things we were talking about last time. So we were partway through our discussion of this theorem, right? That if D is strictly larger than 3 alpha, so remember, maybe I should draw this picture again. Right, so it's below this line, so this D bigger than 3 alpha condition includes the whole long range, effectively long range and high dimensional regime, as well as all except for this one point of the marginally short range high dimensional regime and part of the really effectively short range, not marginally and high dimensional regime, okay? So basically, so we were using this framework, right, where we write our kernel as the integral, like this, and then we define the truncated kernel where we just cut off our integrals at some scale r. Okay, and what we were doing is we wanted to understand the behavior of various moments and so on as a function of this cutoff threshold r. Okay, and basically what we finished doing last time was to show, to do the analysis of the first moment. Okay, so we showed that under this condition, D strictly larger than 3 alpha, that, well, first of all, we wrote down this exact expression for the derivative of the first moment. This is always valid, of course. It doesn't depend on what D and alpha are. And it involved this sum where you sum over all the points in a ball, y, size of the cluster of the origin, size of the cluster of y, indicator that the origin and y are not connected to each other, okay? And what we wanted to show is that in the high dimensional regime, these two clusters behave just like they're independent from each other in the sense that asymptotically to first order, these factor, right? And I should just get this simple asymptotic.
With it power 2 outside, right?
Oh yeah, sorry. Good catch. Yes, that's important. Okay, good. Indeed, so these factor, and I wrote it correctly there at least. If you have this first order asymptotic ODE, it's a simple calculus exercise to see that the solution must look like this, okay? And we'll talk a lot more about ODEs today, and it's somehow one of the key things that these different forms of asymptotic ODEs have different kind of stability properties with respect to how the errors propagate from the ODE into the solution. Okay, and in this particular ODE, we saw you can analyze very easily by just looking at the derivative of 1 over f, and then you just get the ODE with no f on the right-hand side, right? The one that you can just integrate using the fundamental theorem of calculus. And this particular way of doing things meant that this ODE is very stable with the errors. The errors propagate from the ODE to the solution in a very simple way that you can write out, and just knowing that the errors are small is enough to know, just knowing that they go to 0 is enough to get this, the solution behaves the same as if it was a solution to the exact ODE. Okay. And just as a reminder, the way we did this is we said, okay, well, we can write this exact thing as what we want it to be times 1 minus an error. Then we bounded this error. We said it's non-negative by the BK inequality, and it satisfies a bound like this by writing the indicator as 1 minus the other indicator using FKG to bound one term. And then what we did is we used the tree graph inequality, right? Well, we said, first of all, you can just bound this by the third moment, which is bounded by, oh, sorry, this 3 isn't here. That comes when you do the tree graph. If you use tree graph, you get 3 times the cube at the first moment. So you get cancelling factors. You get the cube at the 5th power at the first moment for tree graph. So you get the 5th power divided by the square. So you get the cube in the numerator, the volume of the ball in the denominator. And because essentially the first moment should grow like r to the alpha, that means that the error should go to 0. And then we saw how you can, in fact, conclude in a non-circular way that it does indeed go to 0 and that you do indeed have this scaling.
So that's where you use d larger than 3 alpha?
Yes. Yeah. Yes. Okay. So what I want to do today, I'll start talking about the higher moments and also these spatial moments that are related to scaling limit. And I also want to give you some indication of what's going on in the critical dimensional case. Okay. Good. So let's maybe start by talking about the differential formula for the piece moments. Okay, so by the way, previously we were using general beta when we were doing these computations, and that was because in this bootstrapping argument we took beta less than beta c, did our analysis there, and then took a limit. In fact, now that we have this asymptotic of the first moment, it's going to just be easy to bound all the errors that appear. We're not going to have to do any careful epsilon delta type analysis like that again. We'll just be able to compute. And in particular, I won't need to work with general beta anymore. We can restrict just to beta equals beta c. Okay. So what happens if we look at the derivative of the piece moments? Well, you can think of the piece moments as just the sum over collections of sequences of p points of the probability you're connected to all of them, right? So in general, you'll have something like this, right? Where in this case, maybe I'm looking at the derivative of the fourth moment, right? And one of the contributions comes from 2 points being on the side, actually in the cluster of the origin, and the other 2 points coming from the other cluster that could open up when I open an edge. Okay, so if I just write down formally what's going on, well, I have to, I'll not write the subscripts on the expectations when they're just the obvious ones. I have to sum over points in the cluster and points in the ball of radius r around that point. Oh, and sorry, there should be this beta c r to the minus d minus alpha minus 1 term. That's coming from the derivative of j with respect to r. And what should I get? Well, I need this indicator that y is not in the cluster at the origin, as before. And then I want to say, okay, well, how much do I win? How much do I increase the piece moment by connecting x to y? Right, and of course it's just the piece power of the sum minus the piece power of the original cluster. Okay. So what are we going to do? Well, we're just going to expand this out using the binomial theorem. Right, so subtracting this just means that we lose the first term here in the binomial expansion. Right, so then we have a sum, p choose k, the sum is from k equals 1 to p of k to the p minus k, ky to the k. Okay. Now, what we're going to do is we're going to do the same trick that we often do to exchange the role of x and the origin. So if you do that, what do you get? Well, y will now be summed over the ball of radius r around the origin, just br. And x is now, well, you're summing it over the cluster and it doesn't appear anywhere else. So it's just giving you another copy of the size. So in fact, let me take out this sum, p to k. K equals 1 to p of the expectation y in the ball of radius r times this indicator times, now I get one higher power here, that came from the sum over x, times the cluster of y to the k. Okay, this is this mass transport argument again. Okay, just exchanging the role of x in the origin.
In the second line here, it was indicated from that x is not related to y, right?
But x is in the cluster of y, so it's the sorry, x is in the cluster of the origin, so it doesn't matter which one you do. Yeah. Okay. Yeah. Thanks. Yeah. If you just formally apply the mass transport principle as a letter exchanging operation, then you should write it that way. Yeah. Okay. Good. Okay. All right. So it's going to be helpful actually to extract the terms from the top and the bottom of the sum and write those separately. And what those give you is, the reason to do this is that these are the terms that involve the quantity that would actually differentiate. I mean, they don't quite involve it yet because we haven't simplified yet, but when we take the asymptotics, they're going to be the terms that involve the thing that we're actually differentiating.
So I'm confused. Where is the sum of the x?
Yeah, so it just became this +1 here.
Okay.
It's similar to what we did in the when we differentiated the first moment,
yes.
right? We said, okay, switch the origin was here, make it here, and then the sum over x just gives you a factor of the size of the cluster. Okay, so if we pull out these top and bottom terms, we get here, and use the fact that we can switch the role of the origin and y, it's symmetric. These two terms will be the same up to the, one of them has a prefactor p, the other has a prefactor 1, which is why we get p plus 1. So I get k to the p times ky. Okay. So again, this is just algebra. This is valid always. The point is, under what conditions can we simplify this? Okay, so let's start by looking at the second moments. Okay, and actually, there's going to be a really important difference between the second moment and the higher moments, which is in the second moment, this term doesn't exist. I only have this term, right? I mean, the sum is empty for the second moment. And this is actually going to cause an important change in behavior of the relevant asymptotic ODE. And this is essentially why these log corrections and other bad things that you could get at the critical dimension can only enter at the second moment. And then once you get to the third moment and higher, the ODEs you get have better stability properties, and you don't produce any further logarithmic corrections. Not that I told you how to analyze the critical dimension yet, but I'll say something about that soon. Okay, so
Completely lost with powers of R. How did you go?
Sorry, I missed the -1. Yeah, thanks. Thank you. Yes, that's important, obviously. Hopefully they look correct now. Okay, good. Yeah. Okay, so if we look just at the second moment, we only get, so I'll call this the self-referential term. I'll often call this the driving term and this the self-referential term. And we only, in the second moment, we only get the self-referential term. I'll just write subscript R. Sorry, I definitely don't want to differentiate with respect to P. I'll just write, this means beta CR. Okay, so I get that this is 3 times beta C R to the minus D minus alpha minus 1. Oh, and I also forgot to include the indicator. Yeah. Okay. Now, what we would like to say again is that. With the indicator again. Oh, yeah, thanks. Yeah. Yes. Okay. Now what we would like to say is that when d is bigger than 3 alpha, again, this expectation should just factorize asymptotically, right? So it should be asymptotic to 3 beta c. And we also already know the asymptotics of the first moment, so maybe let me, let me just write that in. So, okay, we get the sum over, over the ball, which cancels with this r to the d. And we get the first moment, which cancels with the alpha. There is a coefficient alpha over beta c from this constant on the first moment. Of course, these two beta c's cancel. And so I get the r to the minus 1, which is not cancelled, times the second moment. Okay? And in fact, given what we already know, it's very easy to justify this. Okay, you just do the same trick as before. You say you write this as what you want it to be. You can use the first moment instead of the asymptotic form of the first moment. Minus times 1 minus an error. That error is again non-negative for exactly the same reason it was before. That it's a BK thing. It's just saying these two clusters, they're always stochastically dominated when I require them to be different than if they were independent. So I always get the inequality in one direction. And then for the inequality in the other direction, you do exactly the same thing as you did before. You say, you know, I write this indicator as 1 minus the other indicator. The term with the 1, I lower bound using FKG. And the term with the other indicator gives me something like this, except it's the third moment here. It's K3 times the intersection with the ball. So I could bound that by the fourth moment. Okay? And then I get something similar in the denominator. But the point is, it's just because I already actually know the order at the first moment, I can just bound these things using the tree graph and they just go to 0 and I don't need to worry about it. Okay? In fact, not only is this case, but also the error satisfies some power type bound in R, right? Because basically, okay, it's something about, you know, you have some powers of R in the numerator, you have some powers of R in the denominator, and you can check the error is small just because these powers, the power in the numerator is strictly smaller than the power in the denominator. Okay, now for the first moment, it didn't matter how small the error is, but for this ODE, it really does. And this ODE is where we can potentially get logarithmic corrections in the critical dimension. Okay, so if you just have this ODE, let me just write it with a general coefficient. F prime equals A over R, is asymptotic to A over R times F. Well, let's write this exactly with some error, right, where delta is some function going to 0. Okay, and of course, you know, this is a very easy ODE to solve. You consider it as in terms of the logarithmic derivative, right? So the derivative of log f is 1 plus the error A over R. Okay, then you can just integrate both sides. So you get f of R is f of 1. You get an r to the a, basically from, if you integrate a over r, right, you get a times log r, and then you're exponentiating, so you get r to the a. And then you get the integral from 1 to r of delta s over s. Okay? So, you know, before we said, in this other ODE we got, which was like a nonlinear ODE with the square, what we saw was that just knowing that the function satisfies the first order asymptotic version of the ODE means that it's actually asymptotic to the solution of the exact ODE. But that's really not the case here, unless this error is sufficiently small. Right, so we'll say that delta is logarithmically integrable, if this integral converges absolutely. Okay, so if this holds with a logarithmically integrable error, then f is asymptotic to some constant, which is just e to this integral out to infinity r to the a. But if the error is not logarithmically integrable, then you have some correction. Okay. Now, what is always true is that if f prime is asymptotic to a over rf, you know, this is quite a strong version of saying that f grows roughly like r to the a. Okay. In particular, this implies that f is regularly varying of index a. So what does this mean? So actually, this came up in my group theory talk yesterday as well. So a function is said to be regularly varying if, when you look at the ratio of f of lambda x to f of x, and you take x to infinity, that this exists. Okay? In fact, it's a basic theorem from this theory of functions of regular variation that if this exists, then it must be equal to, it should exist for all lambda. Positive. If it exists, then it has to be a power of lambda, and this power is called the index of regular variation. Okay? So, when the index is 0, they're called slowly varying functions. Okay? And, you know, moreover, there's a lot of nice theorems about functions of regular variation. I guess, by the way, in order for this to be true, you need some very mild additional assumptions on your function. For example, it being measurable is enough. So certainly if it's continuous or piecewise continuous or something.
But for parabolas, this is an old stuff, right?
Yeah. Absolutely. Yes, but it's not. I think it's not something that's universally known by probabilists. I think it depends what kind of.
Those who use that notion the most.
Yeah, probably. I mean, I guess it's used a lot in any context where you use Tauberian theory, so also in analytic number theory. Yeah, indeed, though, we do use it a lot. I mean, in all this. I mean, Feller is one of the best references for this, for example. Okay. Good. Okay. So this you can think of this differential. This is like a sort of differential version of regular variation, which is stronger than just being regularly varying of index a. Okay. Okay. Good. So maybe I can say already a little bit about, well, okay, so first let me say that our corollary that we already have of this computation, I guess I don't want to erase this. So let me... So a corollary of what we've done is that if d is strictly larger than 3 alpha, then there exists a positive constant such that the second moment is asymptotic to a r to the 3 alpha. And again, the reason is that when we establish this first order asymptotic ODE, we also get a quantitative bound on the error, which decays at least like a power of r, right? And anything that decays like a power is going to be logarithmically integrable, so you'll produce a constant, okay? And again, this constant is just e to the integral from 1 to infinity of r, if you like. Okay, now of delta r over r, sorry. Okay, one thing to notice here is that this constant will be non-universal, right? Because it's actually mostly determined by whatever these errors are on small scales. And so it's something that will be very sensitive if you change the kernel slightly, you'll change this constant It's not something that you should expect to be able to compute. Okay. Good. Okay, so let me start saying something about the critical dimensional case.
So the second moment grows like, when R is very large, grows like much faster than the square.
Yeah, it grows like the cube of the first moment, yeah. And that,
Variance is exploding.
yeah, indeed. So the fact that the second moment grows like the cube of the first moment is an instantiation of mean field critical behavior. So the tree graph upper bound tells you that always the second moment is bounded from above by the cube of the first moment, and that's sharp exactly in the high dimensional regime. Yeah. Okay. So let me just state a theorem quite vaguely for now, and we'll come back to saying a bit more about this later, that in the critical dimensional case, all errors in the asymptotic ODEs go to 0. And later I'll talk about a general criterion which there's just one thing you need to check and it will suffice to make all the errors go to 0. This is actually technically the hardest thing that I prove in any of in this series of papers that I'm talking about. So the interesting thing is the way this works, it's actually a proof by contradiction. Essentially, you assume that these errors don't go to 0. You work under this contradictory assumption for an extremely long time, establishing more and more nice properties of the model under this assumption, until eventually, after like 50 pages of proving more and more nice properties, you reach some contradictions. So I'll say a bit more about that later, but basically, because it's a proof by contradiction, and it does not establish any quantitative rate on the errors going to 0. So the analysis in the critical dimensional case is sort of two-step. You first have this purely qualitative, ineffective argument that tells you that the errors go to 0. But then once you know the errors go to 0, you're in a position to start computing things, right? Because you can do stuff with these asymptotic ODEs. So in particular, for the first moment, as we saw, we actually don't need to know, the errors in the ODE will, be reflected in the errors here. But if you just want to go, for this ODE, you can go from first order to first order. Okay, so in particular, you get that the first moment has the same asymptotics as in the high dimensional case. Okay? Now when you get to the second moment though, you have no guarantee on how fast these errors are going to 0, and indeed they will actually have logarithmic corrections, at least when d is smaller than 6, so that you're really on that critical line. But at this stage, what do you know? Well, you know that the second moment is regularly varying of index 3 alpha. Okay, and what? The second moment's 3 alpha, yeah. Okay, because we get that's the coefficient that we get here, right? 3 alpha. Okay. So the nice thing is that for the rest of the analysis, we're going to be able to work with these regularly varying functions. It's actually just very natural to do all the analysis at that level of generality, actually. And because the higher moment ODEs have better stability properties, this is why, again, in fact, these logarithmic corrections, if they exist or whatever they are, they can only enter at this stage, and then they just propagate in a simple way. So let's see how that works. So let's look at the peace moment for p bigger than 3. Okay, so I still have this expression written down here. Okay, and again, in the high-dimensional case, it's now going to actually be quite easy to justify with some induction on p that all the relevant errors go to 0. And in the critical dimensional case, I'm just telling you that that's true, but let's just go along with it. So what do we get? We get that this is asymptotic to p plus 1 at alpha at the minus 1 times itself. Again, this is plugging in the asymptotics for the first order, for the first moment, sorry. And then we add b to c at the minus alpha minus 1. Again, the r to the d cancels with the sum over y to first order of the sum k equals 2 to p minus 1. P choose k, expectation of the cluster to the p minus k plus 1, expectation to just the kth moment. Okay? Now, to abstract this a bit, what does this ODE look like? It looks like f prime is a over rf plus h. Okay? And, you know, what we're going to want to prove is, well, really the way you do things is you figure out what the answer is going to be, and then you prove that by induction. But let's try to argue, you know, not just jumping straight ahead to the answer. What I expect is that these functions are going to be regularly varying, right? And they're going to be regularly varying of what index? Well, I should get that the pth moment should be regularly varying of index alpha plus 2p minus 1 alpha, right? This corresponds again to the tree graph inequality being sharp. The tree graph inequality bounds the pth moment by the 2p minus 1th power of the first moment. Okay, so this what the case we want to be interested in is where h is regularly varying of, let's say, index b. Okay, in fact, I might depart from my notes, and everything works a bit nicer if you also have a 1 over r term here. Of course, it doesn't matter whether you have one or not. You just shift the index up or down by 1. Okay. Now, it turns out that this kind of ODE has very different behaviors. You have 3 regimes, which is according to the relationship between A and B. Right? So you have A less than B, A equals B, A bigger than B. Okay? And so maybe to understand this, we can actually just solve this ODE, but maybe to say a bit about why you should have this change in behavior. You know, if you only had this term, right, then f would be regularly varying of index A. You know, if you only had the h term, the driving term, then f would be regularly varying of index b, right? So which of these two behaviors you actually have? Well, you take the larger one, basically, whichever one's dominating. And as you can imagine, I won't go into it in detail, but in the boundary case, when a equals b, then you can produce logarithmic corrections and so on. The two terms are fighting with each other, and as always, you get some logs. But let's not worry about that too much for now. Okay, so, well, if you look at this is actually just a first order linear ODE. So you can solve it with the integrating factor, right? So if you take e to the minus a over r f, right? Sorry, times f. Okay, and you differentiate this, you get, just using the product rule, f prime minus a over r f. Right? So, the point is this term here cancels with this term in the derivative, so you get h over r. Right? So, then you can just use the fundamental theorem of calculus to integrate the other side. This is very basic ODE stuff, by the way, but I appreciate that many of us forget these things after some years of not doing it. I've actually been teaching ODEs for 3 years running, so it's been helpful for me with these projects. Okay, so then you just say, okay, f, you integrate this, you move this to the other side, you have the initial condition, so you should get, and really, of course, these integrals are just r to the a, right? So let me just write that here. R to the a, f of 0, let's do it to 1, f of 1 plus r to the a integral of r to the minus a minus 1 h. Let me change that. Okay, hopefully I did that correctly. But you'll tell me if I didn't. Okay, so here you see basically this change in behavior. It's according to whether this integral is diverging or not, right? So in the case where h actually has a larger regular index of regular variation than a, when b is bigger than a, then this integral diverges. And in fact, one of the nice things about functions of regular variation, right, is that if f is regularly varying of index a, which is bigger than -1, then the integral to r is asymptotic to what you would get. It becomes an algebraic operation, right? If this was actually just r to the a, then when you integrate it, I guess you multiply by r and divide by a plus 1, right? So, right, and this is in fact just true. This is one of the basic facts about functions of regular variation. And there's a similar one when a is strictly less than -1, but then you have to look at the tails of the integrals. And in the case a equals -1, it can be quite delicate, and it depends exactly what your function is. Okay. So if you just apply that here, right, you get that this term is asymptotic to, well, the index of regular variation here is b minus a minus 1, right? So I get, in total, I get h. Also, this s to the minus a cancels with this r to the a when I use the asymptotics, and this r to the minus 1 cancels with this r. So I get, in the end, h over b minus a, if b is bigger than a. Okay? Now, I did this in the case that you had exactly this relationship, but if it's only asymptotic, then it works exactly the same way. In this case, you just do the same calculation I just did. So in fact, if you have this asymptotic ODE, and you're in this regime b strictly larger than a, then this implies that f is asymptotic to h over b minus a. Okay? So in other words, what's happening here is that the form of this ODE means that f wants to have regular variation of index the same as h, right? But this coefficient is not enough. Like if you only had the self-referential term, it's not giving you enough growth. And in this context, the function f just gets pegged by this ratio to the driving term h. Okay? So what that means is in this situation, where you have this non-negligible driving term, you get back into this nice stable situation where knowing the ODE to first order determines the solution to first order. Okay, and this is exactly what happens in these higher moments. Okay, in fact, something similar will happen in the boundary case, at least when this integral diverges, although that depends on exactly what h is. Okay, so what do we see here? Well, this guy wants to have regular variation of index 2p minus 1 times alpha, right? That's what it should be if you have the tree graph inequality being sharp. But the coefficient here is p plus 1, which is smaller than 2p minus 1. Okay, so you're exactly in this situation where the self-referential term is not powerful enough, this constant's not big enough for that to cause the growth by itself. So you must get pegged like this to the driving term. So in other words, what you'll get is that this piece moment should be, and this, you know, basically this will be easy to verify by induction. You'll just say, I want to prove inductively that these relationships hold. This relationship is going to enforce the regular variation of the correct index, and then you'll just use this ODE lemma. I'm going to get, well, what's the coefficient here? It's the difference between 1 over the difference between the index of regular variation, which is 2p minus 1, and the coefficient, which is p plus 1. So I'll get p minus 2 times this this stuff here, the driving term. Okay. So now we just have to analyze this like recurrence relation on the first order asymptotics. Okay, and you know, I won't do that completely from scratch, but you'll see if you mess around with this for a bit, it's natural to suppose. I mean, just by looking at the third moment, for example, and the fourth one, you'll quickly see. Okay, what should the form be? Well, it should be that these moments are some sequence of coefficients times this ratio that I mentioned before, that's written up here, of the first moment to the second moment to the power p minus 1 times the first moment. Okay, and indeed you can check that this is very easy to check, that this formula does propagate via the induction, via using this. And what you get is, well, you get a recurrence relation for these coefficients. It's AP is 1 over p minus 2 times the sum from 2 to p minus 1, p choose k, a of p minus k plus 1, a of k. Okay, and it's a funny feature of these things. So I want to stress that the way we understand scaling limits in this work is that scaling limits arise from the asymptotic relationships between different moments, right? So, for example, the fact that in fact the solution to this is 2p minus 3 double factorial. That's not obvious at all. But this is always how we understand scaling limits: is what are the asymptotic relationships between different moments? You're going to get some coefficients there, and those coefficients are ultimately encoding what the scaling limit is. So, for example, the fact that you get these 2p minus 3 double factorial terms it's telling you that if you look at the cluster at the origin and you size under this cutoff measure and you size bias it and you normalize and you take the limit, you get a chi-squared distribution. And basically, these are the moments, maybe after some shift by 1 that corresponds to the size biasing, they're the moments of the chi-squared distribution. But it's also a funny feature of the method that the way you get these relationships between the different moments is always via some recurrence relation, and it's often quite difficult to solve, right? Of course, there are the definition of the double factorial, just to remind you, it's the product of all the integers of the same parity, right? And in our case, they're always odd numbers that we take double factorials of, so it's just the product of the odd numbers up to 2p minus 3. And that has a very simple recurrence, right, that each time you multiply by the next odd number. But it also satisfies many other recurrence relations, right, and this is one of them. And if you want to show this is true, this ends up being related to some generating function identities, basically that the double factorials arise in the generalized binomial expansion of like half integer, the half integer binomial theorem. And if you use those facts and you massage things in the right way, you'll eventually see, okay, indeed, the solution to this is the double factorial. It can be quite frustrating because you can obviously compute this to however many times you want, and it becomes exceedingly clear that it's the double factorial. But actually proving that can be kind of difficult with these funny recurrence relations. Okay, good, but that's how it goes. Okay, and the point is exactly the same thing happens. An important point is that exactly the same thing happens at the critical dimension too. So this same relation holds both above the critical dimension and at the critical dimension. It's just that at the critical dimension, this second moment might be doing something complicated. There might be logs or something. But those just propagate to the higher moments in this way. In particular, you always get this chi-squared scaling limit at the volume distribution, both at and above the critical dimension. You just have to maybe scale in a different way, in a way determined by the second moment. Okay, and again, this is something that comes up repeatedly, where the way to you can always with this method understand scaling limits before you understand scaling factors, and it's for exactly this kind of reason, that the scaling limits are determined by these asymptotic relationships between moments. Those asymptotic relationships essentially always come from this phenomenon, that about these ODEs of this form, where the f gets pegged to h because of the mismatch between a and b. And so you can play this play this game rather again and again for whatever quantities you want, and you can get all the full scaling limit. I'll say about that more in a second. And you never need to know what this is. You just need to know it's regularly varying, which is something you know because the errors go to 0. Okay.
So this case comes mainly when B is larger than A.
Yes.
And it propagates from the second moment and up.
Yeah.
But you have the other cases, they appear also, or?
Yeah, so, well, you can think that these other cases kind of already appear in the second moment in that, you get some errors here and there that you could consider them to be h if you wanted, right? Or even h is 0. But the
general feature for higher moments is B larger than A.
Yes, although this is what makes things work nicely. It's what lets you extract these first order asymptotic relationships without having any control of the errors. You can sometimes do that in this marginal case as well. It depends basically whether this integral diverges or not. And that is something that will come up in the analysis of the marginally short range. So when alpha is equal to 2 high dimensions, you'll get, well, I'll talk about that soon. In that case, you get these driving terms that are sometimes critical and they produce these log corrections. Okay. Okay, maybe I'll talk about that now. So as I said yesterday, so far we've been talking about the volume moments, and I'll say something in a minute about how you extract these. So far everything's about understanding asymptotics in terms of the cutoff, and of course eventually you want to go back to the model with no cutoff that you started off being interested in and prove some things there. I'll come back to that. Let me talk now about how you understand the spatial structure of the clusters. And the point is it's going to be exactly the same technique. There are some additional complications, but it's exactly the same method. Okay, and let's start by looking at so, as I said, in order to understand the full spatial structure of the scaling limit, you want to consider moments where you include some of the spatial information in the moments. Okay? Now, the simplest one to look at will be we take the inner product of x with some vector. You could think just take the horizontal coordinate or something. It's good to do it for a general vector because then you actually prove the scaling limit. Now, if we just did this, well, of course we get 0 by symmetry. Okay, so we don't want to look at that. The first interesting one is the square. Okay. Now, what we're going to want to do is to do exactly the same thing we've done for the moments, which is to write down an exact expression for the derivative with respect to the cutoff, and then try to extract an asymptotic ODE from it. It's a simple asymptotic ODE. Okay, so if I just had this quantity, well, it's, yeah, maybe let me write it like this. So as always, we're looking at the effect of opening up some edge, which has a length at most r, and understanding when we sum over all such edges that could open up, how much am I going to win on average, right? So I have to sum over, let's say z is the point where this edge is going to open from, y is the other endpoint, and x is this point in y. So this is exactly the same as when we wrote down the ODE for the first moment, except now we need to multiply this. So we're summing over x, y, and z with y in the ball of radius r around z. But now we have to multiply by x this inner product. Okay? And of course, as usual, there's this beta c and the r to the minus d minus r minus 1. Okay. So, well, we're going to want to do the same thing. You don't really have to do this, but it does simplify things a bit. We'll switch the order of 0 and z, except we have to be careful that this was really x minus 0, right? And so when you do this, it should become x minus z, right? In other words, it was the displacement between these 2 points. Okay? And what we'll do, and yeah, so there's this indicator here implicitly that 0 and y are in different clusters. Okay? So what we're going to do is we're going to write x minus z is equal to x minus y plus y minus z. Okay?
Y is in BR of 0 now, right? In the sum?
Yeah. Thanks. Okay. So we're going to write this displacement, it basically is the sum of this displacement, and this displacement. And then we're going to expand out this, this trinomial, right? So we get x minus y comma u squared plus yu squared plus minus u squared, if you like, plus the cross terms. Okay. Now, in order to extract an asymptotic ODE, basically the additional complication here is that we have these cross terms. And if these clusters were really independent, then when you take expectations, these cross terms would just become 0 by symmetry. But of course, the clusters are not exactly independent, so you want to say, rather than just talking about asymptotic factorization like before, you also want to say you have this asymptotic cancellation of the cross terms. Okay. So maybe I'll say a bit about how you do that. So, so what you want to show is that this is asymptotic to okay. So the claim is going to be basically that the contribution from the cross terms is negligible. And the contribution from the other terms, you can do this approximate factorization, the same as we were talking about for the moments. Okay. Now, if you do that, this term and this term actually contribute the same thing by symmetry. That's true actually even before you say anything about approximate factorization. So what we would like to be true is that, okay, we get twice the expectation, the first so, you know, when we have one of these terms, one of these guys just contributes the first moment because its spatial information is not there, right? Like if we look at this term, there's nothing about where z is, right? So you just get the first moment. And then you get this same thing we're differentiating squared. Okay? And then you have this other term which comes from the displacement of the edge y that you added in. Right? So in fact, in this term, you get just the square of the first moment. And then you get, well, we've divided by the volume of the ball, right? And we're looking at the asymptotics. So in the end, what you get is the integral over the unit ball in RD of, I'll confusingly use y again, but maybe, hopefully that's not too bad. Y is now a point in RD that you're integrating over. Okay. Hopefully I didn't make any mistakes here. So, okay. So if you believe me that the cross terms are asymptotically negligible, which again is another manifestation of this asymptotic independence, because if they really were independent, they would just cancel exactly to 0. And then this is what you get if these two, from these other terms, if these two clusters were independent.
Why do you have a square of the first moment here?
It's because you have, when you look at this term, right, this is coming from saying what is the displacement of y, and then, but then you're summing over x and z, right, so you have two clusters.
The b in the integration is the ball of radius r?
Of radius 1. Yeah, you should think this is just the limit of, this is the ball of radius 1, but in RD, not in the continuum, right? It's the limit of the sum. But it's true that there should be another factor of r here, right? This should be r squared. Right, so r squared times this is asymptotic to this. Hopefully, if I did it correctly. Okay. Yeah, this is important. Obviously, I would get the wrong answer if I didn't have this r squared here. Okay. So in terms of how you actually bound the errors here, let me just say something briefly about that. The errors that come from these terms, you can bound in a very similar way to how we handled the other moments. You use a variation on the tree graph inequalities where you say basically if I'm looking at these moments, but some of the variables are weighted by how far away they are, you can bound that by sums over trees where you put the same weights on some of the edges of the tree. It's very, very, very similar thing. And then that gives the errors here are negligible for essentially the same reason as in when we were just looking at volume moments. In terms of the cross terms, basically, when you look at these cross terms, like you might have this sum this x and z, and let's say you fix y in the ball, right? And you're looking at x u z minus y. Sorry, x minus y u z u, right? And then you can think you're multiplying by the probability that the origin is connected to z and y is connected to x, and the origin is not connected to y. Right? Up to some scaling by powers of r and so on, this is what you need to control for the cross terms. Okay? But the point is you can just subtract the factored approximation, because if I just have this term, it sums to 0. So I'm just adding 0, right? But once you have this, you're in a situation where actually this is going to be small, and then you can, again, that's something you can justify using basically the tree graph inequalities again. Okay. So, if we look at this asymptotic ODE, this is again in this form that we studied before, except what you'll see is actually that we change which of these regimes we're in as we change alpha, and this is exactly how this transition here from alpha to bigger than or smaller than 2 manifests itself. So it's one of the really nice things here, I think, where these changes in behavior between the different phases, they just, in the end, come down to this very basic fact about the behavior of this kind of ODE. Okay, so why is that? Well, if we look at this term, what is its index of regular variation? Right, well, I have 2 copies of the first moment, so that's 2 alpha. And then I have this r squared. And I guess I'm actually multiplying by this as well, so let me put this here. Okay. So it's alpha, now that I got rid of that r to the alpha, plus 2. Okay. What is the coefficient here? It's 2. Wait, that sounds wrong. I should get that. It's 2 alpha. Yeah, sorry. It's because this is asymptotic to alpha over beta c. Let me put the beta c here as well. Right, so this is 2 alpha. Here the coefficient, this whole thing is asymptotic to 2 alpha. Yeah. Okay, so the coefficient here is 2 alpha. The index of regular variation here is alpha plus 2. And of course, these are equal to each other when alpha is equal to 2. Right, so if alpha is strictly larger than 2, I get that 2 alpha is bigger than alpha plus 2. Alpha equal 2, they're equal. And when alpha is smaller than 2, 2 alpha is strictly less than alpha plus 2. Okay? And this should kind of make sense in the picture that you expect with the change in behavior between the Brownian type scaling and the Levy process type scaling. Because this term is exactly describing the effect of a single jump. Right? So this is saying essentially when alpha is less than 2, which is when you expect to get the Levy limits, that this contribution from the single jump is actually driving the system. Right? And you get, in the end, that there's an asymptotic relationship between this quantity, summing over the cluster of how far you go in the u direction squared, and just how far you go in a single jump, so by crossing a single edge. Okay? Whereas in the case alpha strictly larger than 2, it's this coefficient that wins, and this thing is actually negligible. It's actually small by a power. Right? The function will actually be regularly varying. In all cases of this inequality, by the way, in this situation, f is always regularly varying of index the max of A and B. Okay? So as you cross alpha being equal to 2, you get this change in behavior of what the index of regular variation is, where it swaps from just being from being governed by this term, in which case you get alpha plus 2 in the Levy case, to getting 2 alpha in the Brownian case. Okay. Now, in fact, what happens here in the case alpha equals 2, you're actually in this boundary case. And moreover, this function h is just exactly a power of r. And in that case, you produce a log. And so you get that this expectation is asymptotic to some constant times r 2 plus alpha log r. Okay? And in fact, again, in this critical case, what happens here is that you actually still have that you're pegged to this driving term, but just with a log. And in particular, there's an interesting thing that happens where when alpha is actually bigger than 2, we're back in this situation where we just have, let's say d bigger than 3 alpha, alpha bigger than 2. You get this non-universal constant, right? The same as what happened with the second moment. But in the case when alpha is smaller than 2, all the constants are universal, and that actually still happens at this boundary case, alpha equals 2. It's kind of an interesting thing that can happen where these constants can change whether they're universal or not, depending on which regime you're in. Okay.
So you gave an interpretation, I think I missed it, that this formula has two terms. One is the long-range correlation between two clusters, and one the short-range.
It's not really that this is the short range exactly. It's just this is the self-referential term. Like basically, whenever you have these derivative expressions, you always get a term like this, which is like the function that you're differentiating divided by r times a constant. That kind of always appears regardless. In this case, you also get this driving term, which is basically describing the effect of a single jump. And there's a change in behavior as whether this is relevant or not, where it's marginally relevant, or marginally irrelevant, depending on your perspective in the case, in the boundary case. Does that make sense?
I think so.
So of course, if you just sum over u being some standard basis, you get this claim about the radius of gyration that I wrote down last time. Okay. So what if you want to get full scaling limits? Well, something very similar is going to happen as when we looked at moments, right? In that we'll be able to look at like arbitrary things like this, and we'll get some horrendous recurrence relation in terms of these sequences of exponents. And then, we just have to show that these are the same as the ones you get for the the relevant super process. And one of the funny things about this is you don't really need to know anything about super processes, because in some sense you could define them to be the things that have the moments given by these recurrence relations. Of course, that wouldn't be very satisfying. Let me just say something about what happens in the next simplest case after this one that we just did, which is just to look at still just one point, but higher powers. Okay. I don't think I wrote down what the ODE is for this one, so I'll avoid doing it. But basically, the story is very similar to what happened for the higher moments of the volume. You get you're always going to once you go to the fourth power and so on, you're always going to be in this regime where you get some driving terms that involve, well, there are two different kinds of driving terms. You get the ones from the single jump, like the higher moments of a single jump, but then you also get ones that are more like the ones we had for the higher moments, where it's in terms of the lower moments of the distribution. So in this case, because you have both of those things, at least one of these is always, the one in terms of the lower moments is always dominant. It may also be that the single jump thing is also non-negligible, but the other one certainly is. And you get a recurrence relation for these coefficients. Okay, so what you'll get is that, I guess I already wrote this here, so let me just use it again. You'll get some sequence of coefficients that depend on this vector u times a very similar expression the ratio of this quantity to this one to the power p, just power p, yep, times the first moment. Okay, where again these a's satisfy some recurrence relation. Now in the case of the Levy process, so when alpha is less than 2, you can't really explicitly solve this recurrence relation, but you can write write a formula for the exponential generating function of these coefficients in terms of the exponential generating function of these moments of the single jump, which turns out to be the correct thing for the scaling limit. In the case when alpha is bigger than or equal to 2, which is the Brownian regime, you get that, in fact, these coefficients are just 2p, not 2 to the p factorial, 2p factorial over 2 to the p. Okay? Does anyone recognize these as the moments of perhaps maybe your favorite distribution? I think this is Jim Pittman's favorite distribution. Actually, this came up a lot in Berkeley earlier this year. These are the moments of the Laplace distribution. Specifically, a Laplace distribution of parameter square root 2. Okay, what is a Laplace distribution? You may, I don't know how widely known this is. It's just the absolute value of an exponent. Sorry, it's an exponential times a random sign. So you take an exponential random variable of this parameter and then you just say, you multiply by plus or minus 1 probability of half-half independently. Okay, this is what's called a Laplace distribution. It actually has many other guises. In fact, if I write it this way, it doesn't really explain why you get it here. So, this is telling you in the end that if you do this thing again where you take big X to be a uniform random element of the cluster, and you look at its displacement in the u direction, and you look under the size biased measure, and you rescale appropriately, this converges to Laplace, right? This is always the thing again, that these coefficients encode the scaling limit. This is it. This is in the case alpha at least. Okay, and in fact, you can imagine there's something similar that says that the full distribution of X is a multivariate Laplace distribution, whatever that means. In fact, it's not clear how to define that from this. It's also not clear at all from. This is the easiest way of seeing. You probably know that the moments of an exponential are like a factorial times the power. Here you get that, except there's 0 for odd ones, which is exactly what you'll get if you put a random sign next to the exponential. Now, it is not apparent at all from this description why that should be the scaling limit of the displacement. Okay, but there's another way of thinking about the Laplace. In fact, this particular Laplace root 2 is equal to a Gaussian of mean 0 and whose variance is an exponential 1. So if you randomly pick a variance with an exponential distribution and then you sample a Gaussian with that variance, you get this Laplace root 2. Okay? This also, by the way, gives you the correct way of defining the multivariate Laplace distribution. You just do this with a multivariate Gaussian, with a random variance. Okay, now, maybe you're still thinking, well, why is that helpful? Well, it's because essentially what the scaling limit is supposed to be is this super Brownian motion, right? So maybe I'll say a little bit more about what that is. And I should say, by the way, that this, the way I actually did this was just I solved the recurrence numerically, and I saw it was this, and then I was confused for a while. but actually, it's what I learned, even though I always did it this way, with all these things, even with the double factorial, I always just computed them numerically, and then plugged them into the OEIS, and then was confused. Somehow it would have been much easier to never compute these things numerically and just come up with some heuristic explanation of what the moment should be, and then understand things that way. So why should you get a Gaussian with an exponential random variance?
So now you're taking this on an excursion, and you want to see that this projection is this thing.
Yeah, kind of, but there's some subtlety. So let me give a very brief introduction to superprocesses. Okay. So, as I said at some point in the past, the way you should think about what these superprocesses are is just that they're the scaling limit of branching random walk. So the whole story here, ultimately, in the mean field regime and at the critical dimension, is to say, once percolation is in high enough dimensions, it has the same large scale behavior as branching random walk, which is like the non-interacting version of percolation. And branching random walk has this superprocess scaling limit, so you should get the same scaling limit for percolation. And it's a general feature of these kind of things that you still get the same non-interacting scaling limit at the critical dimension. That very often happens, even though you have to put some logs in to make logs into the scaling to make the limit come out correctly. Okay, so as I said when I introduced branching random walk back on Friday, one way you can think of branching random walk is that you first sample a tree from a branching process, and then you embed that tree into space uniformly at random or using random walks. If you like, these are the same thing. Okay, so the best way to understand the scaling limit, in my view, of these things, which is, I'm not an expert on the history of these things, so I may say something incorrect, but my understanding is that people like Dawson and Watanabe studied the scaling limits of branching random walks through what's maybe most accurately known as the superprocess framework, which is really they want to think of branching random walk as this evolving cloud of particles, and then in the limit you get an evolving measure. So it's like a measure-valued diffusion, i.e., like Brownian motion is a diffusion. So it's a continuous time thing where all this measure is gradually changing and moving around and so on. And this is the superprocess framework. The framework I'm going to tell you about is the one that I think was developed by Jean-Francois Legal. He's not here to correct me if I'm wrong. And this is what he calls the Brownian snake viewpoint on these things.
Well, that's him.
Yes. And so basically this Brownian snake viewpoint essentially is that you should just first understand the scaling limit of the tree, the genealogical tree, and then you just embed it into space using whichever spatial motion is relevant for your problem. So that may be Brownian motion or the Levy process, depending on which regime we're in. Okay? So the first thing is to understand scaling limits of trees. Okay, and this is something where there's a very nice perspective on this that comes from the work of David Aldous as well through what's known as the continuum random tree. Okay, so for us, we're going to want to consider critical branching process trees, there's Galton-Watson trees or Bien-Aimé trees, whatever you want to call them, and it's actually more convenient for the overview to think about a slightly different problem, which is to consider uniform random trees, random plane trees. With n vertices. Okay, so plane tree means it comes with an embedding in the plane, so you have to specify for each vertex, its children come in which order, right? So it's the combinatorial information of the embedding into the plane with a root. Okay. And so, an example would be this. Okay, so so here we would distinguish this from the tree where this vertex was to the right of this one. Okay. Now, the starting point of this theory is to notice that there's a classical bijection between these trees. So these trees are one of the many things counted by the Catalan numbers. Okay, and there are bijections with the other objects counted by the Catalan numbers, but the ones that we'll use are the what are called Dick paths with the y. So what these are, they're just, if you like, random walk trajectories that stay positive and then stay non-negative rather, and then return to the origin. They're allowed to return before and then at some time. So at some time 2n. Okay. So again, these are paths in the integers. They move by plus. They start at 0. They return to 0 at time 2n. They remain non-negative in between, and they move by exactly plus or minus 1 at each step. Okay. So what is the bijection? Well, you just take one of these paths and you squish it together. Okay. So it's a bit easier to see in the other direction. If you have the tree, you can follow what's called the contour of the tree, right? So you just you keep your right hand on the boundary of the tree, and you walk around, and you keep track of how high you are, right? And this gives you one of these Dicke paths. And in fact, this is a bijection, and the way to do it the other way around is you just say, any points on this curve, I draw horizontal lines to the left and the right, and I wait until I hit the curve again, and then I glue those 2 points together. Right? That's what I mean by squishing the whole picture together. Okay? And you can see if you do this, you get a tree. Okay? In this particular example, I guess I would get this whole interval here becomes this edge, right? I would get one edge coming off here. I'd get a path of length 2 from this piece, another path of length 2 from this piece. And then I return back to 0, which means I'm starting a new child of the origin, and then I would just get another path of length 2. Okay? Now, the reason why this bijection is nice, if you want to develop a scaling limit theory, and this, I guess, is the idea of David Aldous, you can take your scaling limits here and then biject back, okay? And assuming you have enough continuity in the operations, which he proved you do, then that means you can define the scaling limit of the uniform random tree, which is something called the continuum random tree, as a function of the scaling limit of a uniform random Dicke path, which is a Brownian excursion. Right, so of course, if we didn't have this restriction about returning to the origin at time 2n and staying non-negative in between, we would just get a Brownian motion. If we required that we return to the origin at time 2n, we would get a Brownian bridge, and the Brownian excursion is what you get by additionally requiring that you stay non-negative in between. Of length 1. Actually, it's convenient to take it to be length 2 for some of the things, but this leads to differing conventions about what you scale by. That can be. Nicola yesterday at lunch told me that he spent I'm sure he was exaggerating, that he spent a year figuring out all these issues about whether to include factors of 2 or not in his book in the various places, and this all comes from. It turns out that this scaling it to have length 2 makes a lot of the formulas nicer, but it's maybe not the most natural thing, so you can do it either way. Okay. So in the end, you take the scaling limit at the random walk, which you can imagine, okay, it's a little bit more complicated than taking a limit of Brownian motion, but you can imagine, to get Brownian motion, but you can imagine it's not too much more difficult than proving invariance theorem. And in the limit, you get this Brownian excursion, which is some, random fractal curve like this. And then you just apply the same operation. So every point, it looks to the right and the left, and it sees how, any point that it can see under the curve, it gets glued to. Okay? And then what you have to argue, which is the difficulty, is that this actually defines a random metric space, which is a tree in the sense of metric spaces. Okay? And of course, you can basically define the metric by saying, you take the shortest path where you're allowed to hop over these identifications, right? But this maybe just leads all the distances to be 0 or something, so you have to be careful about that kind of thing.
Just to be sure, so here essentially you take Brownian motion but kind of condition it to be back at 0 and to be non-negative.
Yeah, exactly.
And under this conditioning, you are non-negative but you are also positive?
In fact, in the limit, you're positive. It's very unlikely that you'll return to... In the discrete, you will return to 0 some small number of times near the endpoints, and you don't see it in the limit.
Sure. Okay, thanks.
Okay. So when I stated my scaling limit theorem the other day, you may recall that it actually wasn't stated in terms of probability measures. I said, you take this cluster, you think of it as a random measure, and you rescale the distances, the Euclidean distances, and then you just scale the whole probability. So you make it not a probability measure anymore. And then I said it converges to the canonical measure of the superprocess. So there's also an associated canonical measure here where you do not fix the size. You have a non-probability measure, and it includes excursions of all sizes. Okay, and this is related to what's called the Ito excursion measure in the theory of Brownian motion. I mean, it just is the Ito excursion measure put through this bijection, if you like, and possibly involving some factors of 2 that you have to be careful about if you want to get your results all consistent with each other. Okay. Good. And the way you could think of that Ito excursion measure, I guess, is that you can run random walk until you first return to 0 or become negative. Let's say you run a random walk until you become negative. Okay, so this is a finite length random walk. And then you can do the same thing. So you can rescale that random walk and just rescale the probability. You don't condition on anything. Just make it into a non-probability measure. And if you pick these so that you get a non-trivial limit, you'll get this Ito excursion measure. And if you want to turn that back into something about a limit in the normal sense of probability measures, then you can do conditioning. But that's something you can do at the end, if you like, after you've defined this canonical measure. Okay. In particular, this canonical measure, it's infinite, but it gives finite mass to excursions of length at least epsilon for any epsilon. So conditioning is actually to have length at least epsilon is something that does still make sense. Actually, the normalizing factor there is finite and positive. Okay. So how do you define these superprocesses? Well, you just first sample this continuum random tree, and then you embed it into space using the spatial motion. Okay? So if you want to think about how that works, you can just think about it in terms of consistency, right? So if I want to define what this embedding is, it's enough to say for any fixed finite collection of points in this continuum tree, I get some finite union of the paths, the simple paths between them in the tree. Each one of these is just it's isometric to just an interval in the real line, right? And so it's easy to define on this kind of tree with just finitely many pieces, what is Brownian motion? Well, you just run a Brownian motion on here, on each segment independently, and then you just concatenate them in the natural way, okay? And this defines a consistent family of measures, so it defines what it means to do Brownian motion indexed by the continuum random tree. And similarly with the Levy processes. I guess you need them to be, if they're not symmetric, then you need to be careful about saying which way round you do the motion, but everything will be symmetric for us. Okay. So, so going back to this Laplace distribution, what we expect is that in the limit, so actually in this work, I'm not proving anything about the convergence of clusters to the continuum random tree, like in terms of the internal structure of the clusters, although that's something I'm hoping to do in future work. But what we should expect is that in the limit we get this continuum random tree, and then it's going to be embedded into space, and in the case alpha bigger than or equal to 2, it's going to be embedded by Brownian motions. Okay, so the fact that you get a Gaussian of evaluated at this exponential time, really what you should think of that as is it's just a Brownian motion at an exponential random stopping time. Okay, so how is that arriving from the scaling limit? It's saying that when you look at the size bias clusters, and you have the origin and again this uniform random point x, this is converging, not that this has been proven, but morally what this is saying is that this is converging to this continuum random tree, and the path from the origin to x is an x1. Okay, now this is not the distribution you get actually if you take this continuous random tree measure and you take a uniform random point in it. You don't get an exponential random variable actually. You actually get like maybe the square root of an exponential or something. It's certainly the square root of some gamma random variable. It's probably exponential in this case, but I can't remember. But the point is actually that our clusters, they have random size, right? In the continuum random tree, this construction, everything I was talking about, is about fixed trees of fixed size, right? Now, when you do the superprocesses, of course, when you consider the scaling limits of branching random walk, of course, those have random size. I mean, you can condition on what the size is, and then you'll get these continuum random trees. But really, they have random size. Now, when you take these canonical measures, that corresponds, I guess, to the size having this Ito excursion kind of law. But actually, that's not, when we do this size biasing and take limits, we're not getting the canonical measures because these are really probability measures, right? So it's a different kind of limit, and it corresponds to taking subcritical branching processes, like with mean 1 minus epsilon, so they're just barely subcritical, then size biasing those, and then taking the limit. And of course, we know what the distribution of the mass is going to be. It's going to be this chi-squared random variable that comes from these coefficients here. So what we need to consider is not the continuum random tree of fixed volume, but it's a continuum random tree whose total mass follows this chi-squared distribution. And this is also what you'll get if you take these slightly subcritical branching processes and you take the limit as you size bias them and then take the limit as the mean goes to 1. And it turns out that when you do this distribution between the origin and the uniform random mark point indeed becomes exactly an exponential distribution. How was I doing this? I did it a bad way, which is to just, okay, there is a exact formula for what the distributions are here, and you can check that when you do this random scaling, you want to basically prove some complicated integral equality, and actually I got Google Gemini to do it. It's very impressive, by the way, this new version of Google Gemini. I really recommend that you check it out. So I just said, can you verify this integral inequality? And it says, well, of course, you can recognize this integral on the left-hand side. It's a modified Bessel function of the second kind. And then you find this identity for Bessel functions in some book about special functions, and it gives you this identity. And actually, the exact page references it gave me were wrong, but but all the identities it wrote were correct actually, and I just had to work a bit harder to find the real references for them. And this indeed verifies these funny facts that if you take a continuum random tree with this chi-squared mass, you get an exponential. Okay, exponential distance between the 2 points. And in fact, more generally, if you take if you bias not just by 1 point, but by n points, and you take the limit, you'll get also a continuum random tree with a chi-squared mass, but it's chi-squared with 2n minus 1 degrees of freedom instead of 1 degree of freedom. And in that case, there is also a really nice distributional equality for what these distances look. You just take the tree connecting the points to be a uniform random, the topological data of what the tree is spanning these points is just uniform at random, and then each length of an edge is an independent exponential 1. So it also works out very nicely. Nicolas pointed out to me yesterday after I asked him about it, there's a much nicer probabilistic way of seeing that you should get these exponential 1s coming out. And maybe I won't talk too much longer about this, but if you're interested, I can tell you about it afterwards. Okay. Good. So this also, by the way, will give you the correct guess as to what this limiting distribution should be in the Levy case. which is just that you get your limiting Levy process, and you just evaluate, you stop it at an independent exponential 1 random time. That will give you the correct guess for what this generating function should be, and then you can verify that it is indeed the solution to this complicated recurrence that you get. Okay. Then in the end, you have to do this thing for general moments, and I won't linger on that any further. But basically the point is, once you know that the errors go to 0, which is in the critical dimension is the thing that's very difficult, from there, you're basically just using and reusing over and over again this basic fact about ODEs that in this case, B bigger than A, that you don't need to know what the errors are, and F will be, the thing you're differentiating will be determined by the driving function to first order without needing any guarantees on how fast the errors decay. Okay. Good. Okay, so I guess in the remaining time today, let me say a bit about how you compute the logarithmic corrections. My plan is to spend the last lecture talking about the low-dimensional case. Okay. Now, as I said, in some ways the most difficult thing about the critical dimension is just justifying that the errors go to 0 in these ODEs. And I'll say a bit more about that tomorrow because it's more related to the low-dimensional story. But for now, let's just take it as a given that everything we did with these, getting these asymptotic ODEs to first order, it just works at the critical dimension. But when we look at the second moment, the error is potentially important because you don't have this dominant driving term. And this is where you're going to potentially produce the logarithmic corrections. Okay, so the point is what we're going to want to do.
Just to make sure,
Yes.
on which line are we now for the logarithmic correction?
It's this line. It's d equals 3 alpha less than 6. Yeah. So the proof shows that the errors go to 0 on the rest of this line here. I mean, this should actually really be mean field, and we can prove this under these perturbative conditions with the Lace expansion. This point is also really mean field in some sense, but I think it should be possible to analyze the rest of this line via this method, but it appears to be quite delicate, and given that we already know how to do it the other way, I'm avoiding doing that for now. I mean, my papers are already long enough, let's say. And there really are some things I don't really know how to do along the rest of this line. The point is when dx3 alpha and is less than 6, we're in the critical dimension, but we're still long range, so we'll get the Levy scaling limits always rather than the Brownian ones. Okay. So how would we do such a thing as compute logarithmic corrections? So basically what you need to do, so you'll recall that the first order form of the ODE that we had was this. This tells you that you're regularly varying of index 3 alpha, but it's not sufficient, in order to understand the logarithmic corrections, if indeed they exist, you need to know what is the error, what is the second order correction, in other words, to this ODE. Okay? Now, the basic way.
When you say here logarithmic, they could be worse than that, or they could.
Yeah, we don't know anything about what they are at this stage. Indeed. Okay. Now, one way in which you can produce logarithmic corrections here is to have that actually. Let's say it's 3 over alpha. And then you have some error, which in our case will be negative actually, that looks like log r. And then you have maybe some more errors that are, let's say, smaller than log r to the 1 plus epsilon. Let's say. These should be logarithmically integrable, basically. This is actually not how this computation is going to work, but let me just say this is one of the ways that logs could appear, is you have this constant over log appearing as the second order correction. Okay? Now, if you have this form of the ODE, you can just do the same thing we did before. You think of this in terms of the logarithmic derivative, right? And well, you get so you get f is f of 1 times the exponential of the integral of all of these things, right? And of course, this term is going to give you r to the 3 alpha. This next term, you're going to get the exponential of the integral of c, or 3 alpha c over r log r from 1 to r. And then there's this that will just give a constant because it's you'll get a similar integral, but it will just converge. So, okay. So, in this framework, if you had an expression for the second order term like this, well, this, of course, this integral is 3 alpha c log r, but it's inside the exponent, so it becomes log r to the 3 alpha c. Okay? This is one way that you might understand how logarithmic corrections are produced. And for some of the other things that is still in this less finished work about the chemical distances and so on, like the convergence to CRT, this is more what it looks like, actually. You get an expansion like this. And of course, in this context, it becomes very important to understand what this constant is, okay, because it actually ends up in the power of the log. Okay. Now, this is actually not what it's going to look like for this for our computation for the volume stuff. Okay. Instead, it's going to look something like this. Let's say equals, 3 alpha f times 1 minus something asymptotic to some constant times f squared over r to the 6 alpha. Okay? Now it turns out if you have this, then you also get a log, but in this case, this constant no longer appears in the exponent of the log. It's this 2, which is important. Okay? And now you can think basically, if you're going to have a log at all, the derivative should look like this, right? So that should mean that this f squared r to the 6 alpha, this is not a proof, but this should be like 1 over log, right? Because that a constant over log rather, right? Because that's not the same constant, but some constant over log. That's the kind of scaling that would produce a logarithmic correction via this analysis. Okay, but you see, this can only happen if f is like r to the 3 alpha over root log. Okay, so for this kind of thing, and this is actually just not an easy to prove ODE fact. And I'll save you from going through it because we've done a lot of ODE today already. But you can take this as an exercise. If this asymptotic relationship holds, and again, the nice thing is you don't need any guarantees on how fast this error is going to 0. In contrast to this, where it was actually important that you had a good enough estimate on this term, because otherwise you might have some sub-logarithmic but divergent corrections. In this case, it doesn't matter how fast this error is going to 0. You get an asymptotic relationship like this. In fact, you even get it with an explicit constant, which is governed by, is a function of this constant and 2 and 3 alpha. Yeah.
Couldn't it be Like 1 over root log, the f squared over part of the 6 alpha?
Sorry, what? This is a root log.
No, but about...
Oh, yeah, that wouldn't produce a logarithmic correction. It would produce something. Of course, I haven't told you why there is a logarithmic correction. So, but if this was like root log, like if this error was root log here, you would get this, which would actually give you not a log, but it would give you an e to the root log correction, which is much larger than a power of log. So what happens here, it's not the power of the log in the error that gives you the power of the log in the solution, it's the coefficient of the 1 over log. Which is quite different to what happens here, where you have this more self-referential form where the error is expressed in terms of the function itself. And then it is the power that's governing the power of the log. Okay. But again, this is a nice calculus exercise. This asymptotic form of the ODE forces this asymptotic form of the solution. Okay. Good. Okay. So what we need to do is, well, we need to show something like this for the second moment. Okay? But the moral of the story is, well, you know, we've been on this whole journey today of computing asymptotics of more and more things. And you can just apply exactly that same method to the error term.
So it's the non-self-referential term that you try to see in the equation up there, right?
It's, well, in the second moment you only get the self-referential term, but what you need is you need to look at you need to look at the error, right? So, you know, we had this you know, the derivative is like 3 alpha r to the minus 1 times the second moment. But it's really this times some error, if you like. Okay? What you do is you write down an exact expression for this error, which we've already done implicitly at some points, and then you just apply our favorite trick. You look at the derivative of the error. And then you show that this satisfies an asymptotic ODE, and it's of the nice form that we know how to do, where you'll get that it's a self-referential term plus some driving terms which are expressed in terms of simpler things, and the driving terms win, so you get an asymptotic relationship. And in the end, this gives you a relationship that's basically this error is proportional to some constant times the square of the second moment over the it should be the cube at the first moment times the volume of the ball. By the way, you know, we actually had an upper bound on the error in terms of something similar, but with the third moment, which is of this order. So the error really is of the same order as that upper bound that just comes from tree graph, but there's some constant here. Okay? But again, basically the way you do this is by just redoing all our favorite thing of taking asymptotic ODEs and then analyzing them, but you just apply this to the error term. Okay? Now, in fact, in reality, there are various quite severe complications compared with what we did before. So you don't really do exactly this. For one thing, like before you understand the error in the second moment, you actually have to understand the error in the first moment first, because in the real expression we had the first moment here instead of this, and that error in the first moment is also going to appear in the error here. And then you have to understand the additional error that comes from the second moment. And the annoying thing is these errors, they involve, they have two contributions. So basically, if we just look at the first moment, because it's simpler, right? The exact expression for the derivative of the first moment, well, it was this expectation size of the cluster at the origin, size of the cluster of y, times this indicator that they're distinct, right? And it was convenient to write this as this without the indicator minus the other indicator, which gives you this. Okay. Now, one nice thing is actually the asymptotics of this, and now, of course, we want to be very careful, so we do need to include the fact that we have this intersection with the ball here. But this is something that is determined by the scaling limit, right? It's exactly taking, take this super Levy process and you look at the third moment, but you restrict one of the points to be inside the ball. This is exactly the kind of information that is determined by the scaling limit. So actually this term we're already happy with because we've computed the scaling limit. For this term, well, we need to write this as the product times the volume of the ball plus the covariance. Okay, that's just, this is just an expansion you can do for any two random variables. Okay, and then really what we do is you want to analyze this covariance by, again, writing down ODE for it, showing that it asymptotically factorizes, that you get this nice form with the driving term, and therefore this is asymptotic to some constant times what it should be.
So you always pray for the driving term to win.
Yeah. I mean, in some sense, it has to. If it doesn't win, it means you get non-universal constants. Well, I guess the constants could be non-universal here, actually, but they're not. The difficulty here is actually that you have this sum over the ball, and this actually makes this function non-differentiable as a function of R. So this is kind of a pain, and in fact, to do this properly, you don't really differentiate this. You differentiate what's called the Mellin transform of this function. You do all your ODE analysis with Mellin transforms, and then you use some inversion theorems for Mellin transforms at the end. So I won't say anything more about that. I'll save you the pain. But it essentially, modulo a lot of annoying technical things. It's the same idea as we already saw for computing the higher moments. I should say, one funny thing in this case is, in the end, these constants, they're expressed actually because there's several different contributions and they have different signs. And all of these constants will be determined by the scaling limit, but they're quite complicated actually. And it's not obvious that they don't just exactly cancel. This is one of the annoying things you have to deal with here, because there's some positive terms and some negative terms. And of course, if they just exactly cancelled, it would mean, well, you hadn't really computed the second order term, right? The second order term is something else that's more complicated. But fortunately, that does not happen. You show eventually that this, this should say this, sorry, it's not the derivative that's asymptotic, this. You get a relationship like this, and this is exactly what you want. That gives you this form of the ODE, and therefore this root log. Okay? So that gives you one of the log corrections that you're looking for. And by the way, one point about this is these calculations actually still have content in the high dimensional case. You are still computing the second order correction to the dynamics. It's this power is no longer 6 alpha, it's actually d plus 3 alpha. That's what it really is. Which in the critical dimension is the same as 6 alpha, which means that the index of these two terms matches, which is why you produce a logarithmic correction. Whereas in the high dimensional case, this is actually just small by a power. So you can compute the second order term if you want via this method, but it's not so interesting. So I think it's a good time to stop for today, and thank you all for listening.
Thank you very much. Are there any questions?
What are you going to do on Friday?
Yeah, my plan on Friday is to talk about the low dimensional case and the 2-point function, the SAC prediction.
Just maybe a general question. So you started by stating theorem on the hierarchical space, and then you said you improved it to ZD. Over there, it's at this stage, the way you present is very general procedure of taking derivative and so on. So what is going through, or what?
Yeah.
How does it go?
Yeah, so in the hierarchical case, I set it up in a way that ultimately was very similar to this, but it didn't transition so well to the Euclidean. It took me a while to have this, in retrospect, very simple. I was trying all these really complicated things to try to push more like what I had been doing in the hierarchical case. But basically in the hierarchical case, I always wanted to consider, instead of just moments of the cluster at the origin or whatever, to consider the sums over the whole box. And this is very nice to do in the hierarchical case because the box is actually a transitive graph. And it's sort of easier to prove that these errors are small because you introduce more averaging. And that was one of the main technical things to get the Euclidean case to work, was figure out ways of bounding these errors without first averaging the random variable over the box. You don't really want to do that anymore in the Euclidean case. It just doesn't work very well. And this led in particular to this bootstrapping proof of the first moment, which is new to this work. It didn't appear in the hierarchical case. So in the hierarchical case, there was just a different, it was actually just completely obvious that these errors went to zero from the two-point function estimates, which I haven't talked about the proof of yet. Whereas in the Euclidean case, that doesn't work. Essentially, in the end, the really important difference between the two cases is actually not the fact that the hierarchical lattice has all this additional symmetry, which is often what we think of it as being important for. Really, the key difference in the hierarchical case is that when you cut off edges at scale r, the clusters cannot leave scale r. They're just forced to remain inside the cluster, so inside that box. So, doing the computations inside the box or in the full space, there's no difference after doing this cutoff. Whereas in the Euclidean case, that's not true. And indeed, in the short-range effective regime, actually, if you do the cutoff at scale r, the clusters actually typically live at some scale much larger than r. So it's really can fail very badly. And it's really, there were a number of places in the hierarchical paper where I was using this fact that when you do the cutoff, the clusters have to stay in the box. I mean, it wasn't formulated quite in terms of this cutoff, but it's essentially that. And this is the thing that really badly breaks. So the interesting thing, though, and this is related to what I'll talk about on Friday with the low-dimensional case, if you just assume that you are in this long-range effective regime, which you can say is basically, when you do these moment computations, you get roughly the same answer if you only sum up to some scale of order r, then you get back into essentially the same situation as in the hierarchical case, and you can import the proofs more easily. But in particular, I would say the proof that you have this kind of marginal triviality in the critical dimension, that the errors do in fact go to zero, this is much, much, much harder to prove in the Euclidean case, and it's really for this reason. It's not because of the additional symmetries you have in the hierarchical, it's because when you do the cutoff, you're actually restraining yourself to belong to the ball. And it's dealing with that problem. Actually, if you're at the critical dimension, but you just assume you have this long edge relevance property, then the proof of marginal triviality in the Euclidean case becomes very similar to the one in the hierarchical case. But if you want to do it unconditionally, which I did want to do, it's much harder.
Well, thank you. Yes, you.
How do you obtain the tail estimate then for the cluster?
Can I talk for 5 minutes on that? Or yeah. Okay. Yeah, that's a good point, because this is an important thing to discuss. And the same computation will work both in high dimensions, where you get the 1 over root n, and in the critical dimensional case, where you get an additional log to the 1/4. So you end up square rooting the root log that you had in the moments. Okay, and basically the idea is that okay, for technical reasons, to justify what I'm about to say, you don't really want to work with the volume tails, you want to work with the Laplace transform. But let's just pretend that we can do it directly with the volume tails. Certainly this inequality I'm about to write down is true. One bound you always have, of course, is if you truncate, you've just made the cluster smaller, so you certainly can truncate and bound. Okay? Now, the idea is that you want to say, when you apply the cutoff at scale r, right, you get this characteristic size, which we'll define to be the size-biased mean. Which is the same thing as the ratio of the second moments to the first moment. Okay? And again, there's this heuristic that the best way to be in a large cluster is to be in the typical large size cluster for one of these cutoff measures. Okay? So in particular, what you can show is that if you take this cutoff to be at a large, the zeta inverse of a large multiple of n, then this is almost the same. Essentially, where I have to pick lambda depending on what epsilon I want. So once I've cut off at this large enough scale, which is roughly governed by this zeta function, then you're not really increasing the probability anymore once you go beyond that. Okay, but the point is, this guy here, if I fix lambda and take the asymptotics of this, I'm exactly in the regime where I can apply my chi-squared limit law. Right, so I can write this, in other words, as the expectation and it's this step, by the way, that's easier to justify with the Laplace transforms than with the tails. But if we assume this works, then we're good. I get the expectation times the size biased distribution. Indicator of this divided by 1 over k, right? Because I have to undo the size biasing. Now this term here, if I fix lambda and send n to infinity, I can exactly get asymptotics for this in terms of the chi-squared distribution. And I don't remember what it is off the top of my head, so I'll avoid doing that. And but basically, you know the asymptotics of this, you know the asymptotics of this, and then you get out the answer. That's essentially what it is.
Okay. So if there's no more question, then we stop here. Thanks again, Tom.
Thanks.